This appendix is on the number system, and we first want to review the various types of numbers that exist. Of course, normally people think their numbers are just 1, 2, 3, or simple fractions, but let's review that very quickly. How did the numbers begin? Well, we were counting sheep and goats and so forth like that, and ownership of things, primarily economics and trade, drove a lot of our original number systems. So we began counting things, the regular integers. Integers are 1, 2, 3, and so forth, all the way up to infinity. And these are finite numbers. They originated in the counting and the measuring and then arithmetic operations. These operations, of course, as you know, are the ability to add, subtract, multiply, divide, and also exponentiate. Means that we take something to some power, like we take 3 and we square it, meaning 3 times 3, or if we cube it, we multiply it by itself 3 times. So this is normally the set of symbols we use for add, subtract, multiply, divide, and for exponentiate. And so 3 to the 5th would be equal, by definition, to 3 times 3 times 3 times 3 times 3, 5 times. Okay, well, after the integers, the positive integers, and defining those, what we next began having to deal with are the negative integers. Where did the negative integers come from? Well, the negative integers came primarily from owing someone something or removing something. So, for example, if you had 2 sheep and you owed someone else 4 sheep, then you had 2 minus 4, leaving you with a minus 2 sheep. You were in debt to sheep, so the concept of debt or ownership. Another way more formally to think of it is you could imagine completing arithmetic operations, and that's the more formal way is actually the better way. So we might have an equation, 3 plus x equals to 0. And what we want to do is we want to find x. And x becomes an inverse for the addition. In other words, we want to subtract 3, but we want to add the number what? We want to add the number x equals to minus 3. And sure enough, 3 plus the number minus 3 gives us 0. A little bit different from subtraction. It is not to subtract one number from another, but to add a number which is then negative. This can be thought of if we think of the number scale, 0, minus 1, minus 2, and so forth. Up here, we can think of adding. We start with 2 and add 3. We would move 3 more steps to the right. But if we think of subtraction, we could think of our 3 and subtracting something as moving to the left. So completing an operation with another number is one way we can extend that. Now, for a long time, 0 was not known. In fact, there's a book, I believe, that's now published on the history of 0. 0, nothing, naught, null. The concept of the 0 number was long in coming, and of course it now forms the basis of our numbering system. You can check, and I believe it was Fibonacci who in the 1200s brought the concept of 0 from the Arabic system in India and Arabia to Italy, and therefore from there it spread into Europe. So it wasn't into the 1200s that we had a number for 0. They were still using the Roman numerals, which didn't even have a 0 in them. And a lot of people would think, oh, if you have nothing, there's no need to represent that. It wasn't apparent that you needed a symbol for that. But of course, it's absolutely essential in this sequence of counting the integers backwards and forwards that we need a concept of 0 or nothing. And based upon that, we can talk about inverses and so forth. Next, we can say what other operations, just as this operation gave rise to 0 and it gave rise to the negative numbers, what operations do we have from division? Well, it turns out that we can take 4 and divide by 2 and get 2. Well, that's nice because we're getting another number in the system that we already have. But what if we had 5 and we're dividing by 2? So 5 divided by 2 gives us a fraction, 2 1/2. Or we could think of 5/7. 5 divided by 7. And what is this? These are called rational numbers. They are numbers that can always be represented as an integer divided by another integer, n over m. So if I can represent any integer over another integer for that number, then it is a rational number. The rational numbers, or fractions, which include the fractions, give us the inverse for a given ratio. For example, let's suppose I have a number a, and I want to multiply by x and get 1. You'll notice that this is very similar to this. I want to seek an x such that this equation is true. Now I want to seek an x so that this equation is true. What is the value of x? The answer is x is equal to 1 over a. Once I have a reciprocal of something, 1 over a, like 1/5, then I can multiply that by any other number like 7 and have 7/5 and get all of the rest of the rational numbers. So I got the negative numbers from here, I get the rational numbers from here, I get 0 from here also. And now what we want to look at are the irrational numbers. The irrational numbers, incidentally, the rational numbers can always be represented by a repeating decimal, like 4.323232, and this will repeat to infinity. And it might be very complicated, like 4.32597322597. But any number that can be represented as a rational number, one integer divided by another one, will always have a repeating decimal that repeats. Sometimes that's represented by putting a bar over the repeating part, and that way we can represent the infinite sequence of that repeating. Next, we want to look at the irrational numbers. These will be non-repeating decimals, and they come from inverse exponentiation, just like this came from inverse multiplication. What we want is we want a to some power b to be equal to something. Might be 1 or something else. How do we find that? Well, we might choose a to be 2, and we might choose b to be 1/2. And we might say, what is this going to be equal to? And the answer is, this is, as you know, the square root of 2. Square root of 2 can be proved to be an irrational number. It's 1.41 and so forth. And this number never repeats. Another example of numbers that don't repeat are the very famous numbers pi and e, and the golden ratio used in the Fibonacci sequence phi, and of course most of the square roots and cube roots and other roots of numbers. These give us our irrational numbers. Next, I'd like to talk to you about complex and imaginary numbers. These arise from the complex and imaginary numbers. Maybe I'll start with just a new sheet here. Incidentally, this is section 44.1 here, talking about the numbers. And what we want to do now in this section is talk about complex numbers. Complex numbers also arise from completing an operation, and the operation that we complete there is where we have a negative number to some power. Let me show you how that arises. Let's suppose we have a minus 1 to the power 1/2. Well, that means we take the square root of minus 1. Well, the square root of a number is that number which, when multiplied by itself, gives you the number that's in parentheses. But there is no number that gives you a minus 1 when it's multiplied by itself. If I look at the entire sequence of all of the numbers, that's minus 2, minus 1, 0, 1, 2, to infinity in both directions, and then I look at all the rational numbers, any one of these integers divided by another integer for all the rationals, and then I look at the irrational numbers, which are the roots where I have any number or any rational number, n over m, to any power, let's say alpha. Then, in fact, as long as this is positive, this is not included in any of those numbers. because all the numbers we have, if we square them, we cannot get a negative number. A positive times a positive gives us positive. A negative times a negative gives us a negative. So it turns out that this was a big battle in the mathematics community. The idea of introducing a new number that's called I. And I is by definition a symbol that means the square root of -1. Now once we can include I, then we can take square roots of negative numbers, or roots of negative numbers, just like we can take roots of positive numbers. And it turns out that that system completes now if we have numbers that allow the symbol I in them. So for example, we could take the square root of -16, and that would be the square root of a -1 times the square root of 16. Square root of 16 is 4. Square root of -1 is I, and the answer would be 4 times I. So now let's practice with our numbers. They turn out that all numbers now can be represented in a complex, in one of these forms, or more generally in a complex form like U plus I times V. This is what is called a complex number. It has a real part and an imaginary part. So let's look at this real and imaginary part, U plus IV. And we know how I behaves. I behaves in such a way that if we take I squared, we get a -1. And of course, there's no number previous to this that would give us this result, because any number, positive or negative, always gives you a positive number. So we have to introduce this new symbol. Now, having the new symbol, we can say a number is either multiplied by I or it's not multiplied by I. This is called the real part. This is called the complex part, the imaginary part. So now our numbers, which are complex, consist of a real part and an imaginary part. And you can add, subtract, multiply, and divide these, and they close into a nice system under all of the operations, which is incredible. So now, for the first time, these numbers close under all the operations: add, subtract, multiply, divide, and exponentiate. So now I can take any number and perform any operation with any other number, and I get numbers back in the system. But that does not happen until I get to the complex numbers. And you can see that that's true, because if I had a -16 and I take it to the 1/2 power, there's no number so far until I got to the complexes that would allow that to happen. So you can take these numbers and multiply them and add them. If I add 2 of them, I might have 3 plus I times 2. I might have 5 minus I times 6. And if I added them, I would get 5, 6, 7, 8. And if I add these 2, I would have, I've got a -6 plus 2. I'd have a minus I times 4, and that would be the result. If I subtract them, then I just subtract the relative parts, almost like a vector. If I multiply these 2 numbers, then I would get this times this. I would get 3 times 5 is 15, plus, just like with algebra, I'd have plus 10I, minus 3 and 6 is 18I, and then we'd have an I times an I, which is a -1 with a minus signs, which is a +1. 6 and 6 is 12, plus 12. And so if I add all of this up, I have 12 and 15, so that would be 27. And I have a minus 18I and a plus 10, so it would be minus 8I. And that'd be the product of the two. Likewise, you should be able to divide 2 complex numbers. The way that that's done is if I take one complex number and divide by another one, if I have 3 plus 2I divided by 5 plus I times 6, or 6I, then what you do is you make the denominator a real number and divide it into both parts. You do that by multiplying the numerator and the denominator by what's called the complex conjugate. That's the number, whatever this sign is, you reverse that sign. So I would multiply both numbers by 5 minus 6I. 5 minus 6I. Well, I can do that because this is 1 I've multiplied the numerator and denominator by the same number. But when I multiply these two numbers together, you notice the cross terms vanish, the imaginary part. This is 5 times 6 is 30i with a plus sign. This is 30i with a minus sign. Therefore, the cross terms, which give the imaginary number, vanish, and I'll get 5 times 5 is 25. And then here is I times I is a minus 1, kills this minus sign. 6 times 6 is 36. So I always get a real number when I multiply by the complex conjugate. Again, complex conjugate of a number z is often written as z star, meaning I take the whatever the imaginary part is and make it negative. When I take this number here and multiply by its complex conjugate in the numerator and denominator, then I'm dividing by a real number, and I multiply these out, divide this real number in, and you can see that I get a complex number, so that this system closes. Likewise, I can do roots and so forth, but that is a little bit more complex. To do that, I need to represent a complex number, and let's now call it u plus I times v. We often use the symbol z for a complex number, and u plus iv or x plus iy is the real and the imaginary parts. That's because we can imagine a plane called the complex plane. Incidentally, all of this that we're reviewing on the complex numbers you should have had in your pre-calculus math. So we can have the real axis here and the imaginary axis here, or the I-axis here. So this is 1, this is I, this is minus 1, this is minus I. And I can talk about a number out here, u plus iv, meaning it has a real part u and an imaginary part v. I can also represent that number as having a radius r and an angle theta. How do I compute r and theta? Well, I use the Pythagorean theorem, so r is equal to the square root of u squared plus v squared. Well, what is that? Well, it turns out it's the square root of z times z star. The number times its complex conjugate will give us always u squared plus v squared, which we could kind of see when we multiplied these two together. It gave us the square of the 5 and the square of the 6 added together. So r is the square root of u squared plus v squared, or the number times its complex conjugate. And that's always a positive number, and it's real. And then I can take the square root of that, and it gives us, by the Pythagorean theorem, this number. Well, what is theta? Theta is, as you know, the inverse tangent of v over u. And therefore, I can take v over u, find the tangent, and write that as theta. Now, what is incredible is this number z can also be written as r e to the I theta. This is the very important part that we need to cover in this review to make sure that you understand these equivalent forms of a complex number. U plus IV, or r e to the I theta. How is that possible? It's possible because we have this new term, r e to the I theta, which I now want to write out for you. You recall that e to the x is by definition 1 plus x squared over 2 factorial plus x cubed over 3 factorial all the way to infinity. It turns out that this always converges because even though a number large like 1,000,000 taken to higher and higher powers, at some point that is always overcome by the power of the factorial. The factorial increases more rapidly than any of the powers of any of the numbers. And therefore, this always converges for positive and negative numbers. What we want to look at is we want to look at it for an imaginary number, an I theta. And we can compute that in the same way. E to the I theta is 1 plus I times theta plus I squared theta squared plus I over 2 factorial plus I cubed theta cubed over 3 factorial plus I to the 4th theta to the 4th over 4 factorial. And it turns out that we can take these and simplify them, and when we do, we end up with 1 plus I times theta plus, now I squared is a minus 1. So this becomes minus theta squared over 2 factorial. Theta cubed is I times I squared, so it's minus I. So this is minus I times I cubed over 3 factorial. I to the fourth is going to be I squared, which is minus 1, multiplied by itself, so it's plus 1. Now you'll notice that you're ending up here with both real numbers and imaginary numbers in the series. So the series consists of 2 parts. Every other term here, which is 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial. And it's going to be, you can convince yourself, minus theta to the 6 over 6 factorial. That's because you get 2 more powers of I, which is a negative sign, plus theta to the 8th over 8 factorial, all the way to infinity. Then you get another sequence multiplied by I, and that's the alternating terms, which is plus I times the infinite sequence theta minus theta cubed over 3 factorial. There's the minus theta cubed over 3 factorial. This next term would be plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, all the way to infinity. You can say, well, gosh, I don't know what to do with these infinite series. Well, these 2 infinite series are these are 3 of the most important infinite series you'll ever see. And even though they go to infinity, how do we talk about them? We write them as special functions. It turns out that this sequence right here is equal to, we'll bring this back here, it's equal to the cosine of theta. This sequence is the sine of theta. So this is cosine theta plus I sine of theta. And that's e to the I theta. This is one of the most important formulas in all of mathematics. And it enables us to take this re to the I theta and break it up into 2 parts, because if we had re to the I theta, you can see it would be r cosine theta plus I times r sine theta. And sure enough, r cosine theta, r times cosine theta is u, so this is u, plus I times r sine theta is v. So we have proved that this is true. And this connects our u and v, which is what you might call the Cartesian versus the rotational or the angular version of a complex number. So we need to be able to move back and forth between this form of a complex number and this form of a complex number. And it's done with this important theorem right here, that the e to the I theta is cosine theta plus I sine theta. And what we have discovered in using the expansion of the exponential, which was good practice, is we have discovered that this is, and you need to learn this, it's just you have to take this for a given, this is the cosine of theta, and this is sine of theta. So when your calculator or your computer is figuring out sines and cosines, it's actually computing this series using a finite number of terms. This is often called, the circle here, where's my circle? This circle is often called the unit circle, because if I write it with an r is equal to 1, I'm only looking at e to the I theta. E to the I theta lives on the unit circle because there's no number r which is multiplying it. There's no number r which is multiplying it. If I multiply it by 2, I'm on the circle of 2 with a radius of 2, but with an r equal to 1 here, this is called the unit circle. So e to the I theta is the unit circle. It's a circle in the complex plane with a unit magnitude. Now this covers all of our complex numbers, and there's one final number that you need to know about, and that's the complex number at infinity. With complex numbers, there's only one number at infinity, and it's all the numbers at an infinite distance out here at infinity. And there's one number at infinity. When we are not dealing with complex numbers but only deal with real numbers, you have a plus infinity and a minus infinity. And we'll talk about infinity more a little bit later.